Good morning. No, that's locked already. And happy spring. It's supposed to be spring today, at least. Let's see, first things first. Lecture notes for today. I'll pass them around. So after last week, we had 3 intense lectures getting everything started. This week, we're going to continue with first a little bit more about biology today, just to make sure that all of you don't run away after the physics. Tomorrow, we are going to do some proper physics and derive the Boltzmann distribution and some related stuff in the general case. And then on Wednesday, before Easter, I'm finally going to get to real proteins. And then I'm going to bring up a little bit, what would you do when you need to do either a simulation or a model or something of an actual protein, and what is that we need to think of. And as you're going to turn out, then fundamentally, it's not really anything different. It's a whole lot more detail. And that's why we started with the simplified cases first. As some/most, hopefully all of you might have noticed, I finally had some time yesterday afternoon and created a new website in Canvas, which is so not an official tool of Stockholm University, but I kind of like Canvas, and I've thought about doing it for years. So I'm a little bit sorry that you're going to be guinea pigs for this new website. I'll make sure that all the material is available on the old website too. If you absolutely love Mondo and feel that you so want to submit all your assignments there, go right ahead and do it. We will handle it. But personally, I fell in love with Canvas roughly 10 minutes after I started editing it. It's like 5 times faster for me to add stuff there. And we might even do some trials with some quizzes and assignments for you, not because it's going to count towards grades, but it could be, well, if nothing else, it could be good formative assessments, so you have a chance to click through things and feel that, do I know the stuff we covered the first 2 weeks? But since I haven't done it yet, no promises. It depends how easy it is for me to do. And while I'm at it there, did all of you get that email I sent yesterday? Okay, good. See if you can sign up with Canvas. If you can't get into either website, it's important for me to know. If you can't get into Canvas, that's probably easier for you, but otherwise, we'll take it as it comes. I also noticed that we had made an error, and Daria, I think, had by mistake said that today was the deadline for Lab 1. I said 1 week, so you have 1 week. So that the deadline to add in reports for the first lab is going to be Thursday, like 1 minute to midnight. And I'm a bit hesitant about that 1 week, because the whole idea with these lab reports is that they're going to be short. Dari and Björn and I, we just want to know that did you understand the concepts and did you follow it? Because if you did not follow it, well, first, I'm going to need to cover it in better detail here, and they will have to explain it better to you. In principle, if you spend 1 or at most 2 hours after the lab, you could, in theory, upload that the same night you did the lab. So the problem with giving you 1 week is that I'm a little bit worried that some of you will take that, oh, I'm going to wait 6.5 days before I start. Don't do that. Spend 1 hour right after the lab, and you're going to be all in sync. And I would particularly recommend that this week, because, let's see, Wednesday, this morning we have lecture stuff, and then after lunch we're going to have a lab, and then tomorrow you're going to have another lecture. That leaves Tuesday afternoon to fill in a lab report if you absolutely don't want to work evenings. And then on Wednesday we have lecture and lab again. But then on Thursday you get an early Easter break. If you fill in everything. So if I were you, I would fill in lab 2 and 3 on Wednesday evening, and be done with it. And then you don't have to think about the university until April 2nd. Yes?
Is it possible to look or start studying the lab?
Yes. You have so the second lab is already up there, but the second lab, and I think all the material for lab 3 is on the old Mondo site. Dara is going to move that to the other side. So you're more than welcome to do the labs at your own pace. If you've already finished the lab, I think in particular if you're doing it early, Dara and Björn will likely be more than happy to help you there too. But you can do all the labs at your own pace if you want to. And I think the only updates they do is that they improve things and they realize some things might not have been clear since last year and everything. But in principle, the lab material is the same as last year, and all that stuff is already available in Mondo. Good. So that leaves today's lecture, secondary structure and amino acid properties. I'm well aware that this sounds like stuff you already know, but what I'm going to try to go through, it's a little bit more detail. And now I'm also going to try to connect this back to free energies in particular. and discuss why things happen. And hopefully we're gonna continue this layering. But before we do that, we are gonna spend some 40 minutes or so with discussion questions. Let's see if this works. We have all of you participating. Otherwise, I'm gonna start going through the entire room again. So what's the difference between Helmholtz and Gibbs free energies in theory and practice? Fun Monday morning exercises, right?
It was mainly that you include the volume and pressure with
Yeah, you could say that's semi-impractical. Well, that is the theoretical difference. But what does that theoretical difference correspond to? You have it, but it's just a formulation. The reason why these formulations are important is that it's related to the concept of ensembles in physics. So if you think of the entire system, what does the pressure and volume correspond to? Sorry? Yeah, well, you change the energy to the enthalpy, but this primarily has to do with whether the system exchanges mechanical work with the surrounding. Whether the surrounding is doing mechanical work on the system or whether the system is doing mechanical work on the surrounding. And mechanical work might sound a bit abstract, but that's every time you have a test tube and the volume in the test tube changes, you are actually exerting a bit of work on the air. So the opposite of that would be a system that only can exchange heat, a so-called adiabatic process. That's not part of this course. And if you can only exchange heat, the pressure and volume, well, pressure multiplied by the difference in volume is always going to be zero if there is no difference in volume, right? And that's also when, so if it's an adiabatic system that only exchanges heat with the surrounding, then we use the Helmholtz free energy. And then you're quite right. In the case when we can exchange, also can do work, or the surrounding does work on us, we end up with the Gibbs free energy. So if you're chemists here, which one is the most relevant for you?
Gibbs.
Why? Well, yes, exactly. That test tubes are everything we do, right? Cells and everything. We do not keep the volume constant. Even you might think the volume is constant. It's not strictly constant. Adding 1 milligram of protein to a cubic meter of water technically changes the volume just a little bit. And now I kind of spilled the beans with the practice thing too, that for most things related to proteins in particular, the changes in volume are so minute that it doesn't matter. But mark my words there, key, most cases, proteins. If you're mixing 1 liter of ethanol with 1 liter of water, you end up with roughly 1.8 liters of volume. And in that case, it's a horrible approximation to assume that the volume was constant in the process. So it's not true for chemistry in general, but it is true for protein-based chemistry. And what that means in practice is that we do this horrible thing that we call it the Gibbs free energy, we call it delta G, and we call it enthalpy, but we never really, I can't remember it now, but I don't think we ever include the PV term in any lecture in this course. It might be part of the simulations. And that's also why we use delta G. And then H, you can say that H for the H in enthalpy is occasionally for Helmholtz, but the point is that all these letters and everything, there is no good standard for it, so that just make sure, if you're using the default letters, you don't necessarily have to explain what it is. If you have the slightest doubt whether you're using the right letter, define what it is. You're more than welcome to define anything you want. All right. Number 2, give some examples of relevant versus irrelevant energy barriers at room temperature. You could probably interpret this question in 2 ways. Let's take a step back then. Why do I even ask this question? Why are there relevant versus irrelevant energy barriers?
Is it like barriers that are relevant are being
Yes, but why do we ask that question? What decides whether the barriers are relevant or not? Yes, and in particular KT in the Boltzmann distribution, right? That the probability of something happening is proportional E divided to delta G divided by KT. So depending on the value of delta G here, we're going to end up with probabilities that are either almost 0 or, well, very close to 1, or they're going to be, well, some sort of intermediate range when we might sometimes be able to pass it and sometimes not. So if the probability is virtually 0 here, that's a barrier that's so large that you will never be able to cross it. And that happens if delta G is much larger than KT. If delta G is much smaller than KT, the probability is going to go to 1. So you could argue that what I meant that there are two ways of interpreting this is, obviously, if the barrier is so much smaller than KT that you can always get over it, it's not really a relevant barrier. But you could actually say if the barrier is much larger than KT, well, it's obviously relevant as a barrier, but the exact height of the barrier is not really important, right? Assuming if you're doing high jump and you're going to jump over a bar that's 10 meters or 50 meters high, it doesn't really matter because I can't jump over it in any way. But whether it's 1 meter or 1.5 meter is probably relevant to me because, well, I used to be able to do 1.5 meters in high jump when I was 20. I certainly can't do it now. And this goes back to knowing your energy barriers and KT. Let's see, do we ask about KT here? No, we don't. So let's ask about that again. What is KT?
0.6
per mole. And how many kilojoules? Sorry? 2.5. No, for your sake, know both values, because otherwise you're constantly going to need to translate. So what are some relevant versus irrelevant barriers? Particularly in the case of proteins, perhaps. A torsion angle is what? It's relevant. And that indirectly means that it has to be roughly in the same, a few kts or something. So it may be maybe 2 to 5 kilojoules, kilocals per mole or so. That's might even a bit high. But so that there are some torsion barriers we can cross and others we can't cross. And that means that we have to care about them all the time. So can you come up with some other barrier that is relevant? Let's start with another barrier that is relevant. Yes? Yeah, so what barrier are you talking about then? An example of a process that might have something in that ballpark. I'll give you a clue, something in water. Hydrogen bonds. Few kcals, maybe 5, maybe 10 kcals. We're gonna come back and talk more about hydrogen bonds, but and again, I don't really care about the factors of 2 because that will depend on the surrounding. But the point is, it's not 1 kcal and it's not 50 kcals. So hydrogen bonds are going to be important too, and that's why we keep harassing you with them, right? There are going to be so many cases where whether a hydrogen bond is formed or not will be important, and both cases are possible. So can we think of some other barriers that are usually not that relevant, either because they're too high or extremely low?
Electrostatics.
Because it is
High.
it is high. So that doesn't mean we can ignore electrostatics, right? But we usually can't get over an electrostatic barrier. If you're talking about something that's 100 kilojoules per mole or 100 kcals per mole even, you're never going to take 2 positive charges and push them through each other. Same thing there. If you have one positive and one negative charge as a salt bridge, that's going to be so strong that the likelihood that you can just break that, it's almost never going to happen. With some caveats that I will come back when we talk about proteins. Lennard-Jones interactions. What do you know of those? So what is the strength of an individual Lennard-Jones interaction? The dispersion in particular.
It's weak.
It's extremely weak, right? That the repulsion part gets strong, so you can't push atoms on top of each other. But an individual Lennard-Jones attraction, if you don't know the numbers, think about things that, for instance, this attraction is the reason why even noble gases eventually condense, and that's going to be at minus 270 Kelvin or something. By definition, that has to be extremely weak. On the other hand, at some point you have lots of them, right, and that adds up. But an individual Lennard-Jones interaction is exceptionally weak. And this is another example of a strong one, is a bond. So you're not going to break bonds in proteins because they're so exceptionally strong. Even angles, they vibrate a bit, but in principle, angles are not particularly important. They might vary between 115 and 125 degrees, but you're never going to take an angle and move it to 180 degrees. The energy would cost too much. So this is really the reason why we focus so much on the torsions, the Ramachandran diagrams, why we talk about Levinthal's paradox. The torsion degrees of freedoms are the most important ones in proteins because they just happen, at room temperature, they just happen to be in the right ballpark where they are relevant. We can occasionally cross them and occasionally we can't cross them. How can you predict what processes will occur? Yes? So sorry, say that again. Van der Waal. Yes, so that is the Lennard-Jones interactions. I will come back to that, I think, on Wednesday. So it's a fortunate or unfortunate case when we use many different terms for the same thing. Van der Waals interactions is in general all weak non-electrostatic interactions between atoms. And part of this has to do with the repulsion at short range, and part of it has to do with the attraction at long range. And then there are, of course, different ways. How do we describe the repulsion and how do we describe the attraction? And one specific form of describing this would be the Lennard-Jones interactions. So you can think of the same thing as electrostatic interactions are all the interactions, right? Coulomb's law is one way of describing them. So I would, and again, this is a bit fussy, but normally I would say when you say Lennard-Jones, this is the way of describing Van der Waals interactions, but a 1 over r to the power of 12 term for the repulsion and 1 over r to the power of 6 term for the dispersion. But people violate that all the time. But so Lennard-Jones and Van der Waals is roughly the same. I'll explain on Wednesday why we use the 1 over r 12 term.
Was the Lennard-Jones a relevant barrier at
So the caveat here is that it depends on what you say. So that the repulsion is obviously irrelevant, right? You can't get atoms to overlap. The weak dispersion interactions, if you look at one of them, it's going to be very weak. So then you can cross it all the time. On the other hand, if they add up, at some point they all start to become important. So it's a bit of a caveat with this question that you have to describe what you mean. I would say when you say irrelevant barriers, if they're too low, they're definitely irrelevant. And if they're too high, it definitely presents themselves as a barrier. So it's up to you, how do you interpret the question? So you could argue that there are kind of three ways you want to classify barriers: significantly lower than KT, significantly higher than KT, or say within within a factor 5 of KT. Because I would actually say the most important ones are the ones that are within a factor 5 of KT. Now, of course, if you're doing things at 100 Kelvin, KT is different. And at 3000 Kelvin, KT is also different. So how can you predict what processes occur?
the formula you have in the probability of something happening?
Well, yes and no. That's probability of individual states or even microstates. It's intimately related to that, but not quite.
Isn't it with gives free energy?
The free energy, and in particular, the difference in free energy. And when do processes happen?
Negative. 100.
When the difference is negative, yes. So the difference Now, how fast do these processes happen on the other hand? That's not the first thing. This link, if you didn't follow it, what this link goes through, it proves that this free energy is the energy available to do work. It's not a super complicated derivation, and if you have this awkward gut feeling that you don't really understand why is it called free energy, follow that link. It's not a very difficult derivation, and that really shows you that the free energy is going to correspond to the energy available to do mechanical work. And that's why we call it free energy. Now, if I show you two processes, one of them, let's see, here's where I start, and one of them goes like that, if that is A, and that is B. If I start out at A, you probably agree that we're pretty quickly going to end up in B, right? If this is some sort of delta G. On the other hand, if we start in A, and if it looks like that, are you going to end up in B? Well, it's going to depend on that barrier, right? We'll come back to that later. So in some cases, if the barrier here is very low, we will go over it. And in some cases, if the barrier is very high, it might take a very long time. So all the free energy says is that in principle, it is better to be there. But that, for it to happen spontaneously, it has to be a straight downhill process. So in this case, we would need to start to go uphill, which we can sometimes do, but not always. But if it's a straight path down, we're always going to go downhill in free energy. Don't worry, I'm going to come back to that when we talk about kinetics. So what is the difference between hydrogen bonds in vacuum versus water? In particular, think of a protein or something. As you probably noticed, these discussion questions are not quite as easy as they were at the very first lecture, right? So this is part of my reason for doing this too. If you feel that it's difficult to follow these, try to look at the lecture in extra time or go through the lecture notes or something. Because I'm well aware that we're pushing you hard and everything, but the more you keep up with the lectures, the easier it's going to be for you. So anytime you have a question with difference, think of one case and then the other case. What is different between them? So what happens when you yes?
In vacuum, you will not have water molecule making hydrogen bonds with your protein. So you have to account for those interactions in water, and you will not account for this in vacuum.
So that the difference is in vacuum, of course, it's a net positive, right? Before you have a specific hydrogen bond, say in the protein formed, you don't have the energy of a hydrogen bond. And when you form it, you have the energy of a hydrogen bond. So that means it's clearly a drop in energy, which is good. And then there are some entropic effects, but they're not going to be quite as strong. If you're having a protein in water, on the other hand, when you first have the protein extended and then the protein folded up and forming hydrogen bonds, as you mentioned, there isn't really a net difference, because when the protein is stretched out, all the parts of the protein will be making hydrogen bonds to water. And then when you fold up the protein, there isn't really any net change in the hydrogen bonds. But suddenly you have the protein forming hydrogen bonds inside the protein. And the waters that previously formed hydrogen bonds with the protein, they now form hydrogen bonds with each other instead. So that the net difference in energy is going to be very close to zero. And in that case, the whole difference is rather going to come from the entropy, which is likely a much smaller difference. But we're going to come back to that too. So what are partition coefficients and why are they useful? Even for protein folding, actually. So partition coefficients was this feature that all of you had used, but you might not have called them partition coefficients. Is that formula, right? So you're inverting the Boltzmann distribution. So K here is some sort of constant of a rate equation or something. That tells you how likely is what concentration are you going to have on the right-hand side versus the left-hand side. That's going to tell you how much product you have versus the components. Or, for instance, how much of a particular molecule are you going to have solvated in oil versus solvated in water. So that the second you know a relationship in concentration or spectroscopy, absorbance or something between two, you can tell how much do I have in state B versus how much do I have in state A. And the reason why that is equal to delta G, whether say RT or KT here doesn't really matter. It's just better we calculate cancel mole. That is because the K is proportional to e to the minus delta G. In this case, I'm going to have divided by RT because I'm measuring a mole. So I'm literally just taking the logarithm of both sides here. And, well, the proportionality here is going to end up being a constant. And if it's a delta G, I don't really care about the constant. So you're inverting the Boltzmann distribution. And by inverting the Boltzmann distribution, I take this. It turns out that the part on the left-hand side you can usually measure from the lab, right? And then I can use that to get the difference in free energy between two states. And you use this all the time, because measuring things in the lab is easy. Calculating delta G is usually very hard. And in particular for protein folding, the reason why we do this is that this way we can calculate, for instance, the solubility in how much does it cost or how much do you gain in kilocals per mole to solvate, say, different small molecules, say ethane, toluene, benzene. And while this is just small chemical molecules, they correspond exactly to various side chains in amino acids. And that is going to mean that we know roughly how much it will cost to transfer different amino acids between water and oil, or air to water, which, as we're going to see today, I think, is very much related to what secondary structures they will form. Six, why are free energies so intimately coupled to experiments? It touches upon two of the previous ones.
The free energy is, or what we get as a result of an experiment is going to depend on the free energies.
Yes, they describe what happens in the lab, right? And that is the difference. Energy, on the other hand, does not. The energy will not always go down in a reaction. You can have there are a bunch of reactions where actually the energy goes up, but the free energy goes down, and they will still happen. So energy is not a good way to measuring what things will happen versus not. But free energy will always decide, are you going to observe something? Anytime you observe something happening, it's because there was a favorable change in free energy. So that leads to the next question. But what if you take, for instance, water? Will water spontaneously boil? It won't, right? But you can take a Bunsen burner and boil water. So apparently it can have a process where there is a positive change in free energy. Does that mean that free energy is not correct?
No, but you need to consider the heat gained by the environment.
Exactly, and I'm burning propane or something, right? So in the universe, you have to expand your system, and at some point you have the entire universe. And in the entire universe, the change will always go down in free energy. So the only reason why the water boils is because I'm burning propane, and burning the propane reduces the free energy more than I use it to boil the water. Number 7. What is temperature? that is an example of a derivation I might ask you to do at some point. I'm not going to do that particular one because that I did here, but mainly because I can tell you start from this equation and work your way through it. So temperature had to do with how much the number of available states, i.e. entropy, changes as the energy goes up. It's the derivative. I'm going to talk more about that tomorrow. And I know this sounds super strange and abstract to you now. It will hopefully be a bit more concrete tomorrow when we look at some plots. But the point is, at this point, this is just a definition. And so I'm not sure whether I should be enthusiastic or sad here as teacher. But remember, before you started this course, you thought temperature was easy and entropy was difficult. And now you're all question marks when I ask you about temperature. So at least you've understood that temperature is complicated. Or rather, it's actually not complicated. But the whole point, it's something we can define. It's a very easy property to measure. And we can simply measure it from this derivative of how the number of available state increases as the energy increases. Which happens to correspond to how hot we feel things are. So how does the hydrophobic effect vary with temperature? We had a plot or two about that last time. If you have the lecture notes, you can even look it up. Lecture 1, 2, 3. So is this plot that says temperature dependence. So why is this important in the first place? As you will find out in chemistry, there are lots of measurements and everything that people do as either as a function of temperature, well, primarily as a function of temperature. And the main reason you want to do it as a function of temperature is that it can help you understand what type of process it is. Which is pretty amazing, because now we talk about doing things in the lab with a Bunsen burner and a thermometer, and then just measuring things. You have absolutely no atomic detail whatsoever in the experiments, and you don't need any fancy equipment. But that can help you understand something very, very deep about the molecular properties of the involved atoms and interactions. So most chemical processes, what happens when you raise the temperature? Say if you're solvating a salt in water or something.
It goes faster.
Faster and easier, and you increase the solubility of a salt. If you look at this diagram, what happens with the hydrophobic effect when you raise the temperature? So how many of you have ever, you've probably done some very advanced biophysical experiments in your kitchen at some point. Have you ever boiled pasta? And what do you typically have in the water when you're boiling pasta?
Salt.
And maybe a bit of oil. So what happens with the oil? When you boil the water, does the oil suddenly partition all over the water?
No.
You can't solvate the oil just by raising the temperature, right? So it actually turns out the hydrophobic effect becomes worse, more pronounced when you raise the temperature. So the solubility of oil actually goes down as the temperature goes up. And the second you hear that something becomes more pronounced at high temperature, you should be able to say something based on the equations we know. And if you have no idea what equation I'm talking about, take a guess.
Free energy equilibrium.
Good. If you have no idea what equation you should use, it's probably 50-50 that it's this one. And if, again, there will be temperature variations of all these terms and everything, but the strongest variation is usually going to be the one that has the T explicitly in it, right? The higher the temperature is, the more the second part of this equation is going to matter. The stronger this one will be. So if a process is very sensitive to temperature, it's likely what type of process?
Entropy.
Exactly. The free energy of the barriers is going to be dominated by the entropy. While on the other hand, solving the salt is likely a process dominated by the enthalpy, because it's less temperature dependent. This is pretty cool, right? You don't need a microscope, you don't need a fancy X-ray solution, and this is how we've been able to say that hydrogen bonds are entropic. You don't need any molecular detail, you certainly don't need computer simulations to say it. All you need is paper, pen. You don't even need to do the experiment yourself, because people have done hundreds of these experiments already. Use somebody else's experiment, look at the curve, and think about it. And this is why these equations are way more powerful than you think. That's actually particularly why I like it, because they're powerful not despite of, but because of their simplicity. If this was an equation with 500 terms, you needed to do a computer simulation, then we would also need to worry about our approximations, right? But there aren't really any approximations in these equations. They're universal, because they don't describe the details of a system. They describe general properties.
But this oil, I mean the,
Hmm?
what was the hydrophobic?
So the hydrophobic effect is the effect why oil is not soluble in water.
Yeah, I see.
Hmm?
But I'm just saying that we were talking about things that become better when we raise the temperature.
Yes, but if you look at that plot, it doesn't become better. It becomes harder to solvate oil in water as the temperature goes up. That is an experimental result. It's not something you can deduce. But because of that experimental result, we can deduce that it's dominated by entropy.
Is it possible to explain molecular? Is there an explanation?
So that has to do with, well, yes and no. So all we can say is that it's entropic. That's the only thing we can say from the lab. Exactly why it is entropic, there I'm for now hand waving. But that had to do with the effect that the hydrogen bonds are so strong. Actually, we'll come back to that at question 13. So wait for hold on a second. But question 9 is also related to it. Why is the hydrophobic delta G so well correlated with the non-polar surface area of a molecule? Do you want to try answer it?
Because that should correspond pretty well with the loss of freedom for the water molecules.
Yes and no. From one point of view, this is a horrible approximation, right? Because it's not like you're forming hydrogen bonds with the surface area. It's not that we can form hydrogen bonds with any atom. But this is an example that simple approximations usually work quite well. So on average, it turns out that the hydrophobic effect is going to correspond, it's going to be almost exactly proportional to the non-polar surface area. Which again, because that's roughly the amount of hydrogen bonds you could form. Rough is the keyword. There are some deviations from it, but they're surprisingly small. That's the other lesson here. Don't try to create an advanced model before you try the simple one. Always start with the simplest possible model. If that one explains your phenomena, there are no brownie points for having a more advanced model. It will just make it more difficult for you to understand the model. But the answer to that question, of course, starts to bring us a bit closer to what you asked for, the model, what happens on the molecular scale. There is something here that is proportional to the surface area. So now we know that it's not just entropic, that we knew from the temperature behavior. we also know that it's somehow proportional to the area, at least the hydrophobic part of the area of the molecule. So somehow it's going to have to do with the interface between the water and the molecule. We're not quite at what you wanted yet, but that will come at question 13. Actually, let's take question 13 right now, so you don't forget it. So there I ask, the book even says that the electrostatics in water originates, did you say electrostatics? You might even say, I would even say hydrogen bonds. So the way I put it, this is a bit of a paradox, that the hydrogen bonds in water, they're of course explained by electrostatics, but the hydrogen bonds are entropic in nature rather than enthalpic. So why do we say that? And that has to do with the molecular explanation to the hydrophobic effect. So if it's complicated, again, let's separate it into multiple parts. Why is there no net change in energy if you solvate some sort of small hydrophobic molecule in water? Shouldn't we break lots of hydrogen bonds?
Because hydrogen bonds are so strong that water will do practically anything together.
Right, all right. The electrostatic interactions are strong. That had to do with these barriers I spoke about, right? We do not want to break hydrogen bonds because it would cost too much. And because you don't want to break hydrogen bonds, we will have to maintain them one way or another at any cost. So that brings us to the first part. We don't break hydrogen bonds, we maintain hydrogen bonds. Does that solve the problem? So what's the second part of the problem with what I said? It's the how, right? How do you maintain the hydrogen bonds? Because we obviously no longer have the partners in the protein or the molecule. The part that would be used to be able to form hydrogen bonds, now there is a drop of oil there. So how do the water molecules maintain the hydrogen bonds?
Making a cage-like structure.
Exactly. They will need to reorient around this molecule and form hydrogen bonds. Basically, if you think of this as the floor, I can form it to the top, left, right, forward and backward, but I can no longer form hydrogen bond downwards because there where I have my hydrophobic solute. This is a more ordered state because I can't form hydrogen bonds in all directions, right? And because it is a more ordered state, as you say, we can even talk about this as a cage-like clatrate structure. But by definition, if it's more ordered, that will do what?
Lower that.
Exactly. And lowering the entropy is good or bad? Bad. And that means that it's going to be a rise in free energy. And that's why it costs free energy to solvate hydrophobic compounds in water. And somewhere here we start getting then things start to become very difficult because these clatrate structures, there are some experimental examples of it, but then it frequently has to be based on very fast laser spectroscopy or something because they're not rigid, they're not a crystal structure. So knowing the structures of these clatrates, that's research that people have done the last 20 years or so. But all the way getting to the point that understanding that somehow the waters must be more ordered, that we can get with reasoning. But exactly what the structures look like, we need very advanced experiments or computer simulations. So let's jump back. So what is the role of epsilon? Or let's start with what is the matrix or epsilon?
It describes the environment's ability to shield electrostatics.
Yeah, so we even call it the dielectric coefficient. And this is very important in, say, condensers or batteries or anything. And a high value of epsilon means that you can either talk about this in absolute terms, or what we frequently do is we talk about epsilon r, the relative one, that is, what is the factor compared to the permittivity or dielectric coefficient of free space, or vacuum even. Air is very close to vacuum. And what is this for water, the relative one?
80.
Roughly 80. So in principle, water would actually be great, say, using condensers or something. And occasionally we actually have wet condensers, not so much for the waters, but with salt and other things. It's just that you don't want it to be conductive, because it's conductive, the ions would slip right through. So why is the wall value in water so extremely high?
Because they're small and very movable dipoles.
Movable in what way?
That they can keep up if the charge moves. And so
And
they
how?
can flip around and always be positioned.
Exactly the point, that the whole water molecule can flip around. And if I ask you to make some predictions here, what would happen at very low temperature? Would epsilon be roughly the same, or would it go up, or would it go down?
Go down.
Why?
Because water less mobile.
And at some point you form crystals, right? So water in crystals is not as movable as it is in free water. Same thing if you go up a lot in frequency, which is not really that relevant in biophysics, but this is a way we can measure where it comes from. At some point the frequency is so high that the water doesn't have time to move with the electric field, and then epsilon will go down too. Sorry, I just answered question 11, my bad. So what is then epsilon roughly inside a protein? Sorry? Why is it 3? Why is it not 5?
Because inside the protein, there's the hydrophobic.
The point is it can be 5 too, right? It can probably even be upwards. Not 10 is a bit high, but the point is that it's significantly lower than water. And it's always going to be above 2, I would say. And that's because you always have electrons. And the second you have electrons, they're a bit polarizable. And the reason why it's so much lower than water, sorry, you might have answered that, but I didn't listen.
Sorry. Is it because the hydrophobic amino acids are in the core of the protein and there's not water?
Well, remember, so why is it so high for water?
Oh, because it can move.
The entire water molecules can rotate, right? So the entire dipoles can flip around. Could you imagine that happening inside a protein?
No.
There might be 1 or 2 hydrogen bonds that can, but in general, you can't take the peptide bonds and flip them around 180 degrees because the protein is packed. And what does that imply for the electrostatic interactions in proteins? Are they stronger or weaker?
They will have a larger effect.
They will have a much larger effect, right? Because you don't screen them. And that's why it's not just the fact that it's not really ideal to have an unpaired ion in water either. But in water, first it's heavily screened that it will interact. All the waters will turn its oxygen against that unpaired ion. Inside a protein, having an unpaired charge, it's horribly bad from a free energy point of view. And if you now compare this unpaired charge, should you have it in the protein or should you have it in water? It's better to have it in water, right? And that will lead to this type of hydrophobic effect that charges in particular virtually never occur inside proteins because it's so bad. Which relates us to question 14 then. What would happen if anyway, if I force a titrator, what is a titratable amino acid in the first place? And in principle, there are lots of amino acids where this could theoretically be the case. In practice, this is roughly identical to the ones we typically call charged, because unless you're moving to completely extreme pH values. We will look a little bit about that today. But what would usually happen if I force, say, a glutamic acid to be on the inside of a protein? In water, it would be charged, negatively charged. Yes? They would typically be protonated, right? So when it's protonated, can you then have it on the inside of a protein? And that means that it's going to be good and everything, and it's not really bad to have glutamates inside a protein because it can be protonated.
It's still bad, but there will be less bad.
So why is it bad?
You don't want charge unless it has a counterpart.
Well, it's not charged, right? Because now it's neutral. Or it costs free energy, right? You're going to pay a lot in free energy to protonate the glutamate. So that there is no way around this. The only question, do I pay it by paying lots of free energy for having it charged on the inside of a protein, or do I pay a lot of energy for changing its protonation state? So it will never be good, but if you absolutely need to put it on the inside of a protein, it might be slightly cheaper to protonate it or deprotonate it first, but it will never be good. Good. Lots of stuff there. What we're going to talk about today is that we're going to move from that super simple case to the real stuff, proteins. And in particular, understand how hydrogen bonds and entropy and enthalpy gives rise to the secondary structure. But before I do that, I'm going to spend just a few minutes on something else. In most of these courses, we talk a lot about modern science, and we virtually only talk about things that are right. That's actually why I've deliberately included some things, for instance, the Linus Pauling DNA structure and everything, that were wrong. Because it also, I think it's important because it helps you understand how science works. So I had dinner with my father on Thursday in Lund. He's a retired professor in medical microbiology, and even we started talking about this, and then I brought up this paper in the course, and he even mentioned that at some point in an interview a few years ago, Jim Watson had even said that, remember how I said that Pauling produced these incorrect structures, right? And Jim Watson at some point said, well, if Linus Pauling had just come by Cambridge and asked us, we would have given him all the data, and then he would likely have solved the structure. But whether that is a rumor or whether it's mostly Jim Watson, that is related to the fact that scientists, we're often too proud, stubborn, and everything to accept that other people might be pretty smart too, or accept that we might be wrong. And that's dangerous, because incorrect things frequently keep, either you publish a paper that's incorrect, or incorrect assumptions tend to live way too long in science. And that is partly related to some other things I'm going to show you. So in the 1960s, some of you might have read this already. In the 1960s, there was an amazing result. And this is actually a real picture from the National Bureau of Standards in the US. Let's see. Small example in a test tube that in Russia, there were a couple of scientists, and in particular, this was confirmed by Deryagin, who was pretty much the most famous scientist in Russia, that Fedyakin had first observed that under some very special conditions, if you put water through very, very, very thin capillaries, this water could somehow spontaneously condense and form a phase with very special properties. You would have a viscosity that is 10 times higher and completely different spectroscopic properties and everything. And they gave this new phase of water a new name called Polywater. So basically the water would polymerize. And this is a real example from a paper by Lippincott from the US, where they too, the US were able to reproduce this a few years later. And they argued that you see all the small water molecules here, right? And then they would argue they would somehow form an extended network of hydrogen bonds, which doesn't really correspond to ice, but it's a much more rigid hydrogen bond network that you would expect under normal circumstances. And this went so far that they were even able to determine quite a lot of properties of this water, that you would have a freezing point roughly around 200 Kelvin plus and a boiling point at 500 Kelvin. And the US were so worried about this that they argued that Russia was on the verge of developing a polywater gap because new amazing properties. I would guess that you haven't read this in your undergraduate physics textbooks, right? And this is, of course, because it's wrong. It's completely wrong. What is wrong with this? You can explain this, and they should have been able to find out. Richard Feynman actually explained this a few years later with the typical very, very simple reasoning. So this, of course, is not completely obvious, right? But what I'm going to, let's do one of these peer exercises again. So talk to the person right next to you and try to understand, can we, based on what we know, and in particular that curve, how the free energy varies of the three different phases, explain why this can't be true. Take a minute, and I might give you a lead if you want. Not entirely easy. Since you're a bit quiet here, I'm going to give you a lead right away. The free energy, the relative free energy between these three different phases, solid, liquid versus gas form water, that determines when you move between the phases, right? Imagine what would happen if you had a new phase with these temperatures. What would that mean for all water? So take your minute now. So the curve just says what is the free energy as a function of temperature for water. And you have a solid phase that is the best at very low temperatures. You have a gas phase that's the best at very high temperatures. And then you have this liquid normal water phase that is best at intermediate temperatures.
Free energy of what?
The free energy of water. So this would be for water, this would be roughly 0 degrees centigrade, and that would be 100 degrees centigrade, right?
Oh,
Yes.
This is by no means I don't think it's definitely a correct answer, but could it be because in this tube, the pressure affecting the water causes the temperature's threshold to change?
For now, I would say let's not even care why, but let's focus on what is wrong with this. It's a completely, regardless of the conditions, it's completely wrong. It can't be right. Sorry? It actually can at the triple point, but not at room temperature. But I think you're getting close to the answer here. Let's try to draw. I so need more colors here. Black. Let's see if that one works. Let's try to draw. Let's assume that polywater was a fourth phase of water here. Try to use those 2 points and try to draw that in that diagram. And we already know that this is 273 and this is 373 Kelvin, right? So we have one temperature at whatever, 523, and let's say that's another one, it's 243. So there is something there and there is something there. So the polywater line would have, the blue one is ice, right? So here you would have the polywater line being better than ice. Because otherwise it would, that's why it is melting. And here you would have the Polywater line be better than the red gas one, right? So that the Polywater line would have to go somewhere there, right? So what would that happen if you compare Polywater with normal liquid water?
Not undergo phase transition.
It would always be polywater.
All water in the world would have to be Polywater, which it obviously is not. So Polywater is definitely not a phase that can be stable. Do you see the power of these equations? We don't have to analyze. I could not care less with what is wrong with that. It doesn't matter. It can't be right. And it's kind of scary that it took Richard Feynman and some other people to realize that it doesn't matter. Because the problem is that if you start arguing about their experiments, you're going to be stuck in the details, right? The power of these equations are what here depended on the detail or the pressure in the tube? Nothing. And because it's universal, it also means that the result is universal. And by the time we've said that, sorry, it's theoretically impossible, this cannot be a correct result. And again, it's discovered in '62, 7 years later, these are fairly famous scientists, they were not stupid, but people kept publishing on this for 7 years. And I think we should have more people sit down with a piece of pen and paper saying, this is obviously ridiculous, it can't be true. Yep.
Could you just go through how you reduce the slope of the line?
I don't know anything about the slope of the line. The only thing I know that at this temperature, the water is the freezing point, right? So that if I'm below that temperature, it's better to be normal ice. And it's above that temperature, it's better to be polywater. And that must mean that the polywater line must have lower free energy when I go from below 243 to above 243, or whatever the point is. That is the definition of a phase transition. Same thing when I'm boiling. Normally it's better to be polywater, but around that temperature, suddenly it must be better to be in gas phase. So then the red line must cross. And then after that, then I just draw a line. I have no idea about the exact line. So, well, I guess in theory you could say that the line should go something like this. I think the likelihood that that happens is fairly low. Because in theory that could happen, of course. But phase transitions are usually smooth. So what do you think happened? So there are actually some papers, and I have links about this in the course. So hey, it's well worth reading this because it tells you something about when science goes wrong. So it likely turned out that when you have a capillary, and if the capillaries are thin enough, the amount of water here is exceptionally low, while the surface area is relative to the volume quite high. So at some point you likely start extracting impurities that might be just on the surface of the glass or something. You might even extract some impurities from the glass. So there were some arguments that when people, it was virtually impossible for them to determine polywater spectra without having a bunch of characteristic peaks of impurities, things related to sweat, for instance, and everything that might be in the air. And this, I think, was one of the lead that eventually put people on the right track, that if it's impossible to determine polywater spectra without the impurities, the polywater is likely more based on the impurities than the water itself. And eventually this died out. There was a famous talk by Langmuir, who's a famous physical chemist, who used this as an example of pathological science. And pathological science, I think, is an interesting concept. It's literally the same, well, it's the same word as we use for disease, right? This is not necessarily, it's borderline scientific misconduct, but it's not really scientific misconduct. Well, we can easily fool ourselves as scientists, and I think that's what happened here too. These were not bad scientists, they didn't want to trick the world. But bad results have a tendency to live on forever. Which of course brings to the next question, what is science? How is science different from, say, astrology? Or creationism? Yes?
It's like everything is just theory, not
No, creationism is certainly a theory.
There's more evidence.
That can be proven wrong.
Exactly. You can't, if you can't prove a result wrong, it's not science. And I think there are certainly people saying this, I say at least that's a good definition for natural science. There are some cases of social science or humanities and everything where you could argue that you need a broader definition. But in real science, I think that is a good definition, that you must be able to prove it wrong. And there's a classic quote by Wolfgang Pauli that's talking about some student that this is not right, this is not even wrong. And the point is, if it's not even if you can't prove you wrong, it's perfectly okay to be wrong. But if your theory is so fuzzy that I can't even prove you wrong, it's not science. So that's, of course, the good theoretical definition. But Polywater was definitely wrong, and it took people 7 years. Yes?
When exactly did we start using statistics in science and physics?
That's a good point. Probably early, sometimes around the Natural Revolution, I would say. We've certainly developed the statistics. So, but the answer you gave is also beautiful and simple, right? So but what if I do an experiment and suddenly I do my experiment on protein folding and suddenly I get one outlier result? That means I should give up all my theories on protein folding because I proved myself wrong. So that's not how science works either, right? Or you realize with, say, evolution, that there are, of course, minor things that we hadn't accounted for and everything. That doesn't mean that we give up on the theory of evolution. So science somehow tends to develop more into research programs. So that, of course, if you prove me wrong or if I reisolate that experiment, I don't necessarily give up everything we thought about, but we try to modify the theory. See, can I incorporate this strange result in my theory and improve the theory to make it better? So, for instance, you could argue that general relativity proved Newton wrong. It doesn't mean that we've given up everything we knew about gravity, but we modified the equations and created a better description of this. But the problem is, of course, that's also how bad science works, right? That when you get a result that contradicts you, you try to modify your theory, you try to get more data. And I think this is the hard part, is that eventually these results tend to die out, but it frequently takes way longer than we would like to be the case. And I think there's another example that I forgot to say that bad theories and everything die out, not because people accept that they're wrong, but because the proponents of the theory eventually die and the next generation of scientists take over. And it's not as incorrect as you might think. So I'll give you one more example. Science is more related to literature than you might think. How many of you have read Kurt Vonnegut? Cat's Cradle, have you read it? So what's Cat's Cradle about?
Water crystal that is different.
Ice 9. Yes, it's a scary ice. So it's an ice, I should remember this, but it's basically an ice form that everything that the ice 9 touches, and it freezes at something like 45 degrees centigrade or something. And if the ice 9 touches it, that spreads to becomes ice 9 too. And I think he even got the idea from Enrico Fermi or something. This is one of his scientist colleagues who actually gave him the idea. It's pretty scary. Could this form of ice exist? Why?
Because then it would already be.
Exactly. For exactly the same reason as the last plot. If that was the case, of course, you could in theory imagine an exceptionally high activation barrier. But in practice, if there was ever one such ice crystal that had formed anywhere in the world, within days at least, all the water in the world would immediately move over to ice 9. The cool thing is that since then there is actually a real ice 9 crystal that we have discovered too. There are tons of different forms of ice. Ice 4 is the normal one. But the real ice 9 only occurs at fairly high pressures and low temperatures, 150 Kelvin or so. But it's another example. You can explain this with the very simple free energy equations. Good. That gives us the main topics of today. Remember what I said, that the F equals E minus Ts equation was not quite as simple as it might look like. It's an amazingly powerful equation, and that's why you need to understand it. And just as we can use it to explain some literature and science mistakes, we can use it to explain and understand a whole lot of things about proteins. So that's my plan today. I'm going to, let's see, it's 10:12. I'm going to get started here with 5 slides or something, and then we're going to get you a well-deserved break. So now I'm going to head back to the polypeptide chain and the secondary structure, but I'm going to try to formulate things with less hand-waving and more free energy than we did the very first lecture. So already now, I don't think I showed you this plot. We talked about the energy landscapes, right? And here too, energy landscapes is a very good model to think about because it helps us understand roughly what happened. And in this case, I'm even going to draw a single one-dimensional landscape. And this is hand waving, but you can think of the landscape as somewhere if we start out here, and on the y-axis we still have energy, and we want to get to low energy. But somewhere along the road here, we could also think of things in terms of entropy. So when we start out, our chain or protein, whatever it is quite stretched out. We don't have a whole lot of favorable interactions yet, but we have a lot of freedom. The chain is very mobile. And as you're moving down this energy landscape to lower and lower energies, and we become collapsed, as we are collapsing the chain, the first step of that would be the molten globule we spoke about last week, right? What happens to the entropy as we collapse it? We become more and more restricted. There is less and less space available to move. And that is bad. And that's the complication here, right? Because again, F equals E minus Ts. A low E is really good, but as we're going down in energy, with these chains, we're also going to go down in entropy. So there are one out of two things that can happen there. Either we go down in energy quicker than we go down in entropy, and then we will somehow be able to find these states, or the energy drops too quickly, and then we're somehow going to be stuck on the way because we can't really move anymore, and the energy barriers are going to be too high. So whether protein folding happens or not is going to be based on a balance between energy and entropy. We need to gain energy faster than we lose the entropy, because otherwise we get stuck. And the way, if we do that in a slightly more realistic fashion with at least a two-dimensional landscape, you frequently see these sombrero-like structures. So in this case, we want to get to the center, whether it's purple or something deep down there, and then we start out here at the green one. So what's going to happen, the native protein is down there in the center, while the unfolded one is, we start out here. And you see the red or the black lines here, they're somehow going to need to cross the first barrier, and then they're going to end up in some sort of intermediate state here. That's what we call the I state. And then depending on what the energies are, we will jump across the second barrier there and hopefully find the native state. But this is then going to depend on how good is that state versus how high is the barrier to the real folded state. And this is just in 2 dimensions. You can imagine how many traps there would be in 100,000 dimensions. And it turns out that we can frequently measure this in experiments. So you can measure these rate constants, and you can identify that there is some unfolded state and there is some sort of native state, and we might be able to identify some intermediate states, for instance, by the amount of secondary structure we have in it. I will show you later today how we can determine that secondary structure. And if we measure this of time, we might also be able to see how fast do we move between the unfolded and the intermediate state, and between the intermediate states and the native states. And well, for instance, based on those rates and the detailed balance, we can actually determine the free energy of these states too. A friend of order would then say, yeah, that's all good and well in theory, but that does work in practice. And it actually turns out that it does work in practice. So this is an example of a curve, I think it's determined from NMR, when we have some very simple reaction coordinates, and we can show that depending on the temperature and everything, the protein will actually spend time in all these different states. The blue one there is going to be the best. But we also spend time in these regions and these regions. You probably can't see it really beautifully there. But this is a completely unfolded protein. That is the completely folded state, and that is some sort of intermediate states. And the way we define these, of course, these proteins would also need 100,000 degree L, at least 10,000 degrees of freedom. So the way we define this is that we might have some sort of spectroscopic probe, so we can measure what is that particular hydrogen bond formed, or what is the distance between these 2 residues with NMR. So we find some examples of reaction coordinates that describe how compact the protein is. But the take-home message here is that this is not just based on very simple theories. This actually works in practice too. So let's go through these secondary structures, but now we're going to think in terms of delta G and identify the entropy and enthalpy for all of them. And we're also going to think about what happens during folding. So before we look at the secondary structure, what is this extended state that we see here at the bottom? So that's an all trans chain of polyalanine in this case. Remember what I said about that on Friday? Is that a good representative of an unfolded state?
No.
Why?
There's only one microstate.
Yes, or you could say that it's just as good or bad as all the other ones, but there are hundreds of billions of them. And the point is that it's not that all unfolded proteins are stretched out. In general, unfolded proteins are going to correspond to this molten globule we talked about on Friday, because we don't want to turn the hydrophobic parts to the water. So if we start with this state and think in terms of energy and entropy, is the entropy high or low for that state? If you just look at that particular conformation. Why? Why is it low?
Because there's only one way
Right.
to be like that.
It's well ordered, right? But if you think of the unfolded state as a collection of all the states that are not, say, helix or sheet. If you think about not just a specific conformation. For that type of unfolded collection of state, is the entropy high or low? High, because there are lots of states like that, right? So the reason why you might want to be unfolded is because the entropy is good. High entropy to be unfolded. I'll come back. There is another caveat there that actually that incidentally also explains why proteins have to be chains, but that we will talk about after Easter. Energy, on the other hand, that's going to depend on the amino acids in the unfolded states. In this particular case, it would be horrible because we would turn all the hydrophobic parts to the water, which would force the water, which would break hydrogen bonds, and then we would require the water to form a clatrate around it, which would be an entropic effect. On the other hand, if these were polar amino acids, the energy would be quite good. So let's move to the secondary structures instead. Alpha helix first. So what happens with the energy and entropy when we form an alpha helix?
Reduce entropy
Why?
because there are very few states that correspond to an alpha helix.
Exactly. So now we need to think macroscopically again, right? On the one hand, all the unfolded states, that's one macroscopic way of thinking for protein, tons of them. Alpha helix, it's pretty much only one. You can't move a single torsion more than a few degrees, then we would break the helix. So it's an astronomical drop of entropy to fold an alpha helix. The reason why we still form an alpha helix is that we end up with all these beautiful, the yellow dots here, the hydrogen bonds. So it's a well-packed structure, and there are tons of hydrogen bonds formed in it, which is particularly important on the inside of a protein. Because on the inside of a protein, we would otherwise need to turn these oxygens and polar hydrogens to other hydrophobic residues. And for a normal alpha helix, we also always have this pattern of I to I plus form forming hydrogen bonds, which means that every single, both the hydrogen and the oxygen in every single peptide bond, apart from a few at the very start and a few at the very end, would be involved in forming hydrogen bonds. Alpha helices, it actually turns out that alpha helices and titratable amino acids, they frequently occur together. And the reason for that is, an alpha helix is very simple, but it's also not as simple as you might think. So one property of the alpha helix is that it's periodic, right? So you turn 3.6 residues per turn. So 3.6 residues later, you're going to be back on the same side of the helix where we started. So this is a small sensor that is part of a membrane protein. I will cover this more when we talk about membrane proteins. But inside this membrane protein, you have this particular helix is actually going to move up and down when we change the voltage across the membrane. And then there are a bunch of charged amino acids here, actually arginines. And do you see how they sit on the same side? And because they sit on the same side, they can kind of form a sort of step ladder thing that they can gradually move from one point to another and swap hydrogen bond partners with each other. Yes? So titratable amino acids were the charged ones. The ones whose, I usually call them titratable because they're arginine, lysine, glutamic acid, aspartic acid, and histidine. And another way would be to call them charged, but they, as I say, in the inside of the protein, they might not be charged. and rather to have to constantly explain that they might not be charged. Calling them titratable amino acids is an easier way. Let's see if I even have a movie of that. I don't remember. Yes. So do you see in this particular case that the entire structure is moving? I'll come back to later on why it moves, but this turns out, do you see that it made a jump, and that aspartic acid here that previously was interacting with that one is now interacting with that one. This happens inside your cells every time you conduct a nerve signal in your nerves. And it happens in like 200 microseconds or something. And in your hearts too, all the time. This is the basic of voltage-gated ion channels. And the reason why I'm showing this already now is that see that the entire alpha helix here actually stays intact all the time. We don't unfold the alpha helix, so we can have this protein undergo through a fairly large conformational change here, but you have the entire secondary structure element moving. You don't break the secondary structure, you don't refold the protein, but by having some conformational changes up in the loop, I can take this entire helix and move it either up or down. And it moves like 1 or 2 nanometers. Which does not sound like a lot, but it's probably the most fascinating miniature machine in the world.
The green alpha helix seems to unfold and fold.
It might, yeah, oh, you mean that part up here? It probably does a little bit. This is the membrane protein. So the ones we care most about are the ones in the membranes. So why do you think the alpha helix doesn't unfold? We're forcing it to go through fairly major conformational transitions, right? Wouldn't it be reasonable to think that it could unfold?
Because it's very unfavorable to lose hydrogen.
Exactly right. It's stabilized by all these hydrogen bonds, and we would pay an insane amount of free energy by starting to break the hydrogen bonds. There are a couple of different ways you can draw the alpha helix. I kind of like this because it's a good way of understanding that you need to know that the pattern in a normal alpha helix is this residue I is hydrogen bonding to residue I plus 4. It's a very characteristic pattern of an alpha helix. And what happens with these other helices is, again, 413 is alpha. If you squeeze the helix harder, you're going to move so that residue I is bonding to residue I plus 3, and then it's a 310 helix. And if you squeeze it looser, you would have I to I plus 5. Which with this pi helix. Forget about the 217 helix. And what I didn't show you at the previous slide, but it's pretty cool, I will show you that again. What actually happens when this undergoes a transition is that right here in the middle, there is actually a small part here when the helix moves over to a 310 helix, right in the middle. Can you imagine why it would, you probably don't see it that well here. Why would it like to move over to a 310 helix? It is not not an entirely trivial model. Remember what I said about the alpha helix? How many residues per turn are there? 3.6. In a 310 helix, how many residues per turn are there? So if you can actually draw something called a helical wheel. So if you draw the helix here, we draw residue, say 0 there, and residue 1 there, and residue, say 2 there, residue 3 there. This is not that good. And then it would be residue 4 there, and residue whatever 5 there. So you see that would be offset. That would lead to the spiral stairway. On the other hand, if we have the 310 helix, with a 310 helix, there are exactly 3 residues per turn. So we would start with 0, 1, 2, 3, 4, 5, 6, 7. No, sorry, I screwed up there. I drew that as 4. But you see the point, right? So that if you have a protein like the one on the previous slide, in a 310 helix, these charge side chain would be exactly superimposed on each other. So if you have an alpha helix, if you're going to move this up and you're going to need to have one charged hydrogen one charged side chain take the place of another one, you would also need to rotate the entire helix. And that's problematic because all these side chains are interacting with other stuff. But if it's a 310 helix, they are exactly on top of each other, and then you can just move the helix vertically. So normally a 310 helix is not as good as an alpha helix, but there are a few places where it's sterically very convenient to have. But we'll come back to talk about membrane proteins. But that's the point there is just that under some conditions it can actually be more favorable to have in particular 310. 516 is very rare, and 217 I've never seen. So you probably already saw this, but that's again just to stress the part that I said that while the hydrogen bonds are important, it's important to remember that this is not what an alpha helix looks like. This is our beautiful way of representing it. It makes sense to us, but the way it actually, this is still a collection of atoms. And to really understand this, you're going to need to look at every single hydrogen bond and the rest of the chain here. So is it only the hydrogen bonds that matter for the alpha helix? So if it was only the hydrogen bonds that mattered, all residues would always form alpha helices, right? Which they obviously don't do. So what else is required to form a stable helix? Sorry? Sorry? Yes, but what is required of the residues to form a stable alpha helix? Well, they need to form peptide bonds, but again, all amino acids form peptide bonds. Sorry, you said there was something here. I didn't listen. I didn't hear at least. Periodicity, but well, so if I just take prolines, that's a periodic sequence. So they should not clash, right? And they should all these torsion angles throughout this helix, they need to be in regions where there is no steric clashes and where the protein is fairly happy to be with the angles that correspond to alpha helices. And that's not universally true. So if we look at, that's why we have these Ramachandran diagrams, is that some regions, the right-handed alpha helix here in particular, are better for some residues than others. And if you have a particular residue that is not happy here, it's not going to like to form an alpha helix. And that is the case, for instance, for proline. Proline does not like to be here. Why doesn't proline like to be there? It's bulky, right? And it has this built-in ring. We'll come back to that after the break, I think. But then I have another question for you. This doesn't make sense. If you look at glycine, is glycine bulky? Glycine's Ramachandran diagram is more spacious than any other Ramachandran diagram we know, right? Glycine can be almost, there is no other residue that can be in so many places in this Ramachandran diagram as glycine. But glycine doesn't like to be in alpha helices. Why? Well, flexible is good, right? Flexible means that it can definitely be there. Yeah, but I can form that with the hydrogen bonds.
Too small.
Well, small is good if you want to fit something. If you want to fit something in a hole, the smaller the better.
It loses its flexibility.
Well, now we're getting closer.
It loses entropy.
It loses entropy, right? Because glycine is so small, when it's not in an alpha helix, it can have much higher entropy than other residues. And now we're suddenly going to take this very flexible residue and force it to be stuck in a very small part of the Ramachandran diagram, which is suddenly just as small as the other ones. So for glycine, the drop in entropy when it moves to an alpha helix is more severe than for the other residues. And that's why glycine doesn't like to be an alpha helix. So this is kind of cool. The reason why proline and neither proline nor glycine like to be in an alpha helix, but they're completely opposite reasons why they don't want to be in an alpha helix. For proline, it's because of the steric clashes. For glycine, it's because we would force it to lose too much entropy. It's actually 10:30 now, so rather than me storming on to beta sheets, I would suggest that let's take our 30 minutes and reconvene here at 11 sharp. And then we'll talk both about beta sheets and then turns and a couple of other things. Because glycines are important for some things in life. All right. Beta sheets, beta sheets, beta sheets. They are completely different from alpha helices, which I hope that you agree with. Rather than me going, there are a couple of things we already touched upon here. One thing has to do with how we form the interaction, global versus local, right? So in this case, there are still tons of hydrogen bonds, and just as alpha helices, most or virtually all peptide bonds here are going to be paired. There are going to be some ones at the end of each sheet that are not formed. The other thing that I might have mentioned, but that becomes a little bit more important now, the beta sheet nomenclature is well known. The beta sheet nomenclature is well known, and the beta sheet would be the entire collection of all these polypeptide backbones here that form a large extended sheet. What is not quite as common, you might, is the beta strand. And when I say beta strand, I typically mean one of these chains, so just the second chain here that forms a beta strand. So one obvious thing is that if you look at one beta strand, it's the same issue as with the alpha helix, right? An individual beta strand corresponds to that completely stretched out, well, pretty much unfolded amino acid. And that is an exceptionally unlikely conformation from an entropy point of view. There is only one way to put it there, is that's to stretch out the chain in all trans. So individually, that is a horrible conformation. The reason why that exists is, of course, is that when you have multiple ones formed like that, they can suddenly form hydrogen bonds between themselves, and that pairs up all the hydrogen bonds in the structure. First things first, where are all the side chains pointing? Actually, exactly. So either towards you or into the plane here. So they're going to be, you have one plane formed by the entire sheet, and the side chains point out of that plane in both directions. So if we think about the beta sheet here, what are some important differences going to be when you form a beta sheet? So I didn't explicitly cover that for alpha helices, but for the alpha helices, how does an alpha helix form? And I'm going to go through this in much more detail in a few days. Yes?
It's going to form when there's a certain specific
Right, but I'm not so much thinking, I'm thinking like how it forms, right? That we need to place these amino acids and we need to form the torsions so that we start forming the spirals there. And when we put the first residue there, it's bad because we only lose entropy. When we put the second there, it's still bad. When we put the third there, it's still bad. And when we put the fourth there, it's still bad, and then we put the fifth there, then it's I to I plus 4. Then we start gaining our first hydrogen bonds. So you can already now, we can say there's going to be a bit of an uphill battle initially when we form an alpha helix, and by the time you come to 4, 5 or something like that, then we're going to start gaining energy because we form hydrogen bonds. If we look at beta sheets, what's going to happen here? So the point is, that we need to put this entire backbone in this conformation, right? And when we start by putting a backbone in this conformation, there is still no gain. And then we need to put an entire second backbone in that conformation too, which is also very unlikely. But when we do that, we don't just gain one hydrogen bonds, but then we gain, 1, 2, 3, 4, 5, 6, 7 hydrogen bonds. So already here, and we're going to see this later, you can kind of start to that it's going to be probably more of a barrier here because there are more residues we need to put this way. But once we get to the top of this barrier, it's going to be a very strong form. So it will likely take longer for beta sheets to form, but that's still a bit of hand waving. I also mentioned that there are two ways of putting these. And here's where it helps if you can draw your amino acid backbone. So you have NC alpha C, NC alpha C, NC alpha C, NC alpha C, and then the hydrogens and the oxygens pointing out. So this chain is going in that direction. And here we have a chain in the same direction, NC alpha C, NC alpha C. So this chain also goes in that direction. And to pair up all the hydrogen bonds here, you see that these hydrogen bonds are going to be a bit, well, not tilted, but they're not going to be completely straight. So they have to point in slightly different directions, which is reasonably okay. But it's not quite as good as if I take this chain that goes left to right, and then I pair it with another chain that goes right to left. So here we have NC alpha C in that direction. And when they go in different directions, you see that all of them are going to be perfectly paired up with each other. So this will be just so slightly better. But both of them are good, and both will happen. There is another reason I would argue why the top one is slightly more likely. So that we have names for this. The first one, the lower one would be called two parallel sheets. The top one would be called anti-parallel sheets. Yes?
The bottom one goes in the same direction.
Well, what's bad with that?
There is a large distance between those fragments in the protein chain.
Exactly. So that when I'm at the end of the right here, right, I need to find something else for me to go out of the whiteboard or something and form a completely different helix or whatever, some other structure, so that I can come back there. And that will definitely take a bunch of residues. It will depend whether that is a loop or alpha helix or something. And that means that it's going to be a longer drop in the helix between these two sheets. While when they're anti-parallel, I can go in one direction, and then you're going to see that I can turn around pretty quickly, and then I can go straight back. So the anti-parallel ones is like drawing a pen. You can just go up, down, up, down, up, down, up, down, which is a bit better. The other thing that happens with beta sheets is that because of this, because of the way the backbone looks, they're actually going to be a bit zigzagged or pleated. So that, and this is hard to, you can't see this in the simple schematics, but if you look at the residues, it's going to be a bit of that effect. But here we see more clearly, the yellow dots here are the side chains. So what do you see with the side chains here?
Every other of them.
So remember the pattern I told you about the helix, that there is a pattern of say 3 to 3.6. Here there is a pattern which is every second. Can you imagine using these patterns anyway? Nature will use them. So in particular, let's start with a beta sheet, that might be easier. So if you take a long stretch of beta sheets, and then we make every second residue hydrophobic and every second residue hydrophilic. Then you're going to have one very hydrophobic side. The upper side here would be hydrophobic, while the lower side would be hydrophilic. Which is kind of a neat way to separate things. You would effectively have a surface where one side of the surface is hydrophobic and the other side is hydrophilic. I'll show you how to use that shortly. And I also mentioned that these sheets will be just a bit twisted. On the one hand, this is a small... The reason for this is that you're going to see it all the time in structures, and I want to explain why it happens. So when you just look at the simple model and even the previous slides, this looks so plain, simple, completely beautiful sheets. Anytime you see this in proteins, they're going to look on the right. You see that the entire sheet is turning a bit, right? And that is not something special based on the protein or something, but what happens is that inside each of these strands, the torsions here, they're going to be placed so that it's almost exactly trans, but they're not exactly 180 degrees. So they might be 178 degrees or something. And for one or two amino acids, it's not going to matter. They will look completely stretched out. But when you end up repeating this lots of times, right, you're going to slowly going to turn from that completely straight part. So what's going to happen is that if you start here, you see that you're always turning slightly clockwise if you move in the direction of the sheets. So you're slowly turning. And when you then combine this into a larger sheet, it's going to mean that the entire sheet will actually have a bit of this turning property too. So exactly the direction here is not important and everything, but that's why you look inside any protein structure, the sheets are never going to be completely planar, or at least that's very, very rare. So with that, we know a bit of the unfolded state, we know a bit of the alpha helices, and we know a little bit more of the sheets. But there is one thing I've ignored. We also need to move between these secondary structure elements. And I think all of you most of you at least have taken the bioinformatics course, and occasionally when we try to predict secondary structure, you might try to do a three-state prediction. So you try to predict helices, beta sheets, and coil. And coil would be everything else that's unordered. But that's not exactly how it works. So in many cases, in particular if you have these large anti-parallel sheets, if you have these very short turns, actually sorry, this is a parallel sheet, that's better. Here, if you have a very small turn here from the end of one strand to the next one, that's not really going to be a long loop. You want to make these as short as possible. And nature does that. So these turns, they're so short that they're almost part, they're not just almost, they are effectively part of the beta sheet. So if you are here, if you're having one chain going here, it turns out you can put one residue here and then one residue there. And if you put them in specific Ramachandran torsions, it means that within two residues in the turn, you can end up with the chain going the other side. And this is just slightly different Ramachandran torsions of the turn. But the point is you can have this very, very, very efficient, super well-packed things with just two residues. And then there turns out to be a number of different turns you can do, but type 1 and 2 by 2 are by far the most important ones. So you just need two residues. Can you imagine what residue is really convenient to have in turns? When it's this tight and very well packed. Yes, why? And here you need the steric, there is simply not a whole lot of room, right? You don't want to push in large side chains or anything here. But it's, of course, it will still be an entropic drop for it. But it's happier in turns than any other residue. And we need these turns to be able to fit, to have any sort of continuous sheets. The reason for having this slide is that these turns are so well known. So occasionally when you predict secondary structure, you actually call it a four-state prediction. So you predict helices, sheets, turns, and coils. So you separate the turns from the coils because it's fairly, we can recognize this when there are lots of beta sheets and then there are suddenly two glycine residues and then more residues that are likely beta sheet, then we know that it's a turn in the beta sheet and then you go back. The reason why secondary structure is important is that we can determine it. We can determine it with fairly simple measures. One way of determining would, of course, be to determine the full structure of a protein with X-ray crystallography or cryo-EM. Why don't we do that? Too expensive and too slow. And the whole point of understanding, if you already have the entire 3D structure of a protein, there is no point. We want secondary structure for two reasons. Either because we really, really would like to see quickly what this protein is, or we might want to see that what happens if I change the temperature here. This is actually some very nice techniques to see what happens during folding. But if I want to examine what happens during folding, then by definition I'm going to be changing things, right? And I can't, one of these cases might be at room temperature and another one might be at 60 degrees centigrade. I can't determine a cryo-EM or X-ray crystal at 60 degrees centigrade because then I don't have crystals. So by far the simplest method to do this is CD spectroscopy, which stands for circular dichroism. Remember in lecture 1 that all amino acids are chiral? And the chiral property of amino acids will turn out that if you send circular polarized light on them, they're going to twist this light slightly different in the left versus right hand direction, depending on the amino acid and in particular the amino acid surrounding. And this surrounding is determined by the secondary structure. So you measure this in a fairly complicated method called ellipticity. And it's not important exactly how you measure it, but the point is that depending on whether a structure is alpha helix, beta sheet, or random coil, as a function of the light wavelength, you can end up with different patterns in these CD spectra. Do you have any idea how long this takes or how costly it is? Yeah, it's like 1 minute. And there are probably 20 CD spectrometers in this department. If you don't have a CD spectrometer, we might have to buy one, and it's a low-end one is probably a few 10,000 kroner or something. They're very cheap instruments, and they're very efficient. Because then I can take the same sample, heat it to 50 degrees centigrade, and put it back in the CD spectrometer, and then see whether anything changed. And if my helix now unfolded, it will have moved from the red curve to the blue to the cyan there. So it's super fast, simple. The drawback is that I have no idea whatsoever about sequence. The only thing I will know roughly what is the fraction of alpha helix versus random coil versus beta sheet in the sample. So it's a poor mass technique, but very efficient. Slightly more heavy-handed is to do NMR spectroscopy with chemical shifts. And the main advantage of NMR, then we can get a sequence resolution. So I can actually get a fairly accurate result. What is the secondary structure in this sequence as a function of the amino acid sequence? So why don't we do that all the time? Yes, so we have we have a multiple NMR spectrometers in this department, but it's suddenly an experiment that takes a day. It's complicated to do. You probably need to spend a week analyzing the data, and you need more protein for it and everything. It's not worth it. So which one would you use in practice? Any other suggestions? Exactly. 20 years ago, people would use CD spectroscopy. Today, you just predict it with bioinformatics. So how accurate are secondary structure predictions today? Yeah, 85 to 90%. But again, shouldn't we use experiments so that it's 100% accurate? Exactly. The point is, the reason why we can't really, it's hard to get to more than 90% no matter what method you use. Because at some point you get to the end of the helix. Where is the end of the helix and the beginning of the coil? Again, plus minus one residue there can easily make 5% if the helix is 20 residues long, one residue is 5%. That's going to depend on temperature, it's going to depend on the surrounding, it's simply not that well defined. So for all intents and purposes, 90% is as good as you need to be. So today we don't, unless there is an exceptional case where it's really important and the prediction methods are bad, today just go into the computer and let bioinformatics predict it. It's good enough. So if we compare helices again, helices are formed entirely by local hydrogen bonds, while sheets are non-local hydrogen bonds. The helix can grow, I didn't say that explicitly, I hinted that it can grow fairly fast, but the point is it can grow gradually. You can add one residue at a time to an alpha helix once you have the first few turns. And the initiation barrier, you just need 4 or 5 residues to have formed the first turn in an alpha helix, and you can gradually start adding to it. Beta sheets, on the other hand, either you have a sheet or you don't. You can't add, it's very hard to add one more residue to a sheet. And this also means that there's a very high barrier because you need to take 2 entire strands and put them in completely stretched out manner, which is very bad entropy-wise. And it's not until they actually have formed all those hydrogen bonds that you're going to start to gain anything. So already here we can predict that it's going to be a fairly high initiation barrier, and beta sheets are going to be quite slow to form. And later on in the course we will actually show that this is even a phase transition in most cases. There are also different amino acids that prefer to be in helices and sheets. Helices in particular hate proline because proline is going to be if you put proline in here, proline is going to break at least one of the hydrogen bonds that keeps the helix together. And you can see that. How do you see that in a structure? It will kink the helix because just to fit that round, it's going to be a 10-15 degree kink in the helix. And this is so strong, so you can even see this evolutionary when there are families where some members have had a proline, all of them will have that kink, even the ones that don't have the proline. Yes?
Usually the kink shows pi helix in it?
It depends. No, I wouldn't say pi. Well, it has to do with the definition. So when is thing a helix, right? When are things a helix? So the pi helix in particular had to do with this pattern, whether you have 5-16 pattern in the hydrogen bonds. And in the particular case, you're right in the sense that it's going to be unwound a little bit. But since you don't really have that hydrogen bond, I personally would not call it 5-16 helix. And the rest of the helix, both before and after that, is the standard 413 hydrogen bonding pattern. But you're right that it's a bit unwound. Beta sheets, on the other hand, have a much better tolerance for glycines because they like glycines in the turn from the end of one sheet to the next one. And they also have a bit more room to fit a proline inside the beta sheet, although proline itself is fairly happy to be in loops too. And apart from that, you've gone through the bioinformatics. There are other sequence patterns, so that many of the small and hydrophobic residues actually prefer beta sheets too. Let's see, we already talked about proline being rare in helices. We talked about glycine being common in turns. some residues are very common at helix ends. I think I have a slide about that later on. And we also have, yes?
Apart from the proline and glycine,
Hmm?
the R groups are not the, like, really that deciding whether it's going to be helix or braid sheet.
Well, they are. But for proline and in particular glycine, for some of these residues, the pattern is so strong that one residue can pretty much destroy a helix. Or it will be in the end of the helix. For other residues, there are certainly residues that prefer helix or sheet. But nature also has some sort of built-in stability to random mutations. We will talk about that much more later on in the course. So one single mutation in an alpha helix with a residue that kind of prefers to be beta sheet is usually not enough to disrupt it. It's not good, but it's not completely going to kill the helix. So virtually all residues have a preference for either helix or sheets or turns.
But where does that preference come from?
It's a combination of steric hindrance and how much, steric repulsion in the Ramachandran diagrams, how much it likes to be there. And in part also how good it is at interacting with other residues in the surrounding, either in the 3.6 repeat or the twofold repeat. So how do you think we know this? Yes, or simple, just statistics, right? Homology would mean that they would have to be related, but you can also just count. Look at all alpha. That's actually one of the starts of bioinformatics, so-called the Chu-Fastman rules. That Chu and Fastman started to look at all the helices and beta sheets and all the structures that had ever been determined, and for every residue, like how likely is it for this residue to be in helix versus how likely is it for this residue to be a sheet. And from that, you could infer by the Boltzmann inversion, right, that there's some sort of delta G. Does this residue like to be in helix or sheet? And then you essentially do a running average over roughly 4 residues. And based on that, they could predict secondary structure with amazing accuracy. I think it was 35%. So that's the reason. I think the book even goes through Chu-Fastman. So you can laugh at this. But in the 70s, this was pretty darn sexy. And even when I started these courses in the early 90s, Chu-Fastman, we went through and did exercise on Chu-Fastman. The reason for measuring, can you imagine the advances that bioinformatics have gone through? We moved from 35 to 85% in 2 decades, simply with better methods. Yep.
But how correct would you be if you just guess everything is coil? Wouldn't it be more than 30%?
No, so I think Chu-Fastman is probably, most things are helices or sheets. It might have been, I might have been too low, it might be 45%. The point is that for proteins in general, there are both a lot of coil and helix and sheets. It's probably a bit over a third of each. Chu-Fastman might be 50% or something, I don't remember. But the point, it's clearly better than random, but it's very far away from what you can do with bioinformatics today. So what we're going to go have a look at some of these differences and see whether they can be useful. So the first thing that we can look with all the amino acids is look at their relative abundance. So here you see the abundance here is exactly the fraction, let's see. This is exactly the fraction that they occur in proteins. What was that determined from again? We talked about that. Codon frequency in the genetic code. This has nothing to do with proteins or homology or anything. When you predict them, you might rely on homology and everything. But the abundance itself is just based on nature. We can also calculate the delta G for solvation. In some cases, when this is extremely high, it's even hard to determine this accurately. But these numbers are so high. Again, compare this with KT. So this is kcal. So KT is 0.6, right? So this is 100 KT. So the likelihood, there's e to the power of 100. The likelihood that they would like to prefer to be in oil instead of water is 0. It doesn't happen. But then there are also going to be patterns with some of these, whether they prefer helices or not. So let's start with the obvious ones. Proline first. The problem with proline is that, well, it's not a problem. Proline has this ring. After the C alpha, you move out, and then the last carbon here binds back to the nitrogen. So normal nitrogen would have a hydrogen here, but in proline, we have this ring formed. And that is exactly the hydrogen that would need to participate in the hydrogen bonds in the peptide group. So the proline is missing that. Technically, proline is not an amino acid. If you really, this is not something that's going to decide it, but it's called an amino acid. And the Department of Useless Knowledge. This means that proline is not really happy either in helices or sheets. It's somewhat happier in sheets than helices, but it's turns or coils or something. It is hard to pack this efficiently with anything. Glycine in particular is exceptionally small and flexible, which on the one hand means that it can fit almost everywhere, in particular in turns. The caveat there to remember for glycine is also that means the second you actually do put it anywhere, we do an astronomical loss of entropy, which is bad in particular for helices. And then alanine is the first real chiral amino acid. Alanine is, you could argue that alanine is boring, but boring is good if you're an amino acid. Alanine can fit pretty much everywhere, either helices or sheets. It's a bit hydrophobic and it's a bit hydrophilic, pretty much almost plus minus 0. You can easily have alanine on the surface of a protein. You can easily have it on the inside of a protein. For nature, this is an awesome building block that you can fit pretty much everywhere. And then you start to be larger and hydrophobic. Remember the point that I said that you don't necessarily need to know all these amino acids by heart. So what is the difference between valine, isoleucine, leucine? They're larger than alanine and hydrophobic. If you want to, in terms of understanding the structure, that's enough. Yes, at some point you would need to look up and maybe draw them or something. But in your gut feeling, you only need to know that, oh, now you start to have something that's big and bulky. So they're not, you're going to have a side chain that absolutely doesn't, it's definitely hydrophobic. It's bulky, so you somehow need to put it on the inside of a protein. You will not be able to fit it in turns. Can you have it in a helix?
Yeah.
Sure, if this side of the helix is facing the inside of a protein. You can always have it in a sheet too, if it's on the inside of a protein. And the way we enumerate all these carbons is that the first one would be the alpha, you know what the alpha carbon is, and then you just continue in the Greek alphabet, beta, gamma, delta, etc. So when you say beta carbon, that's just the first actual side chain carbon. But they're pretty boring in the sense they're just hydrophobic. They don't do anything, those carbons. So that's why we don't really, that's why we group them. Cysteine is a somewhat hydrophobic molecule, but cysteine is important. So cysteine contains the sulfur group, or thiol group. The important thing with cysteine is that under the right conditions, you can lose that hydrogen and form a bond between two sulfurs if you have another partner cysteine group. And that's actually, that's not just, it's not like a hydrogen bond or anything. That's a very tight covalent bond, and when you form it, it will not break. And you use that all the time in the experimental lab, and you do the cysteine scanning and everything, because if you place cysteines in the right place, you can check whether these bonds are formed, and if these bonds were formed, even if you don't know what the structure was, right? Where I placed my two residues, they must have been close in space, otherwise this bond would not have been able to form. And then you can get a structure like that. This looks completely boring. What on earth do you think this is? Random coil? That would be my bet. Let's give it a bit more detail. Still completely unintelligible. It's just a random piece of amino acids. So you see here, you have some cysteines here. So here you have two cysteines, one cysteine in that green chain and another one in the blue chain. Do you see that they formed a cysteine link there? And here you have one in the green chain and one in the orange chain. It's another cysteine link there. And here you have one in the orange chain and one in the blue chain, and they formed a third cysteine link there. So this is a protein that doesn't really have any secondary structure. It might be a tiny amount of beta sheets on them. But what all those cysteines do, they create a very rigid, almost knot-like structure. So that if it was not for those cysteine bonds, this would be a random coil. But with the cysteine bonds, they form a very well-defined and strong structure. And it's even called a cysteine knot. This is used in spider toxins. There are lots of tarantula spiders and everything, which tends to hit the voltage-gated channels in your nervous system. It's a very classical example of a fold. And again, this would not be a fold without those cysteines. Some of the ligand-gated ion channels are even called cis-loop receptors because there is a specific cysteine disulfide bridge in the structures. So these structures are usually very important. And they form, so if you, again, they form, this might seem obvious here. So we have one chain here on the left with the cysteine, and then one chain on the right with the cysteine. Then you, for each cysteine, you have these torsions, the first torsion and the second torsion in the side chain, and then we can call them prime on the other side, the first torsion in the side chain and the second torsion in the side chain. What will a cysteine bond or bridge due to the entropy of the system? So this will be a fairly dramatic reduction of the entropy, right? Because you have two chains that in principle, think of the cysteine, not the toxin I showed you. Two side chains that are in principle completely free and flexible, and then you lock them in completely relative to each other, so they can't move at all. So if there's a gigantic drop in entropy, can you say something about how much energy we gain or lose from forming this bond? We need to gain a lot of energy for forming this bond, right? Otherwise it would not happen. Tryptophan is another friend. There's a big and bulky residue, but it's not just hydrophobic. So you have one part of the tryptophan that has this polar part, an NH group there, and then another 6-member carbon ring. So one 5-member ring that is a bit polar, and then a 6-member ring that is a bit bulky. And it's an indole group, the polar one, if you really want to go into the details. This is a very difficult to pack residue. And you do scannings here in experiments too, that if you think you have a binding site or something, you can try to mutate an alanine for a tryptophan, because the tryptophan might fill up the entire binding site and then you might not bind there anymore. So if you want to test by pretty much trying to put something large in a protein, we always do to tryptophan. And tryptophan is pretty cool. So tryptophan is part of the world's smallest protein, which is called the TRP, or the tryptophan cage, by Anderson. So how do you define a protein? So that this is difficult definition with everything. I would say that things become a real protein when there are some residues, when there's a well-defined structure, and there are some residues that are entirely inaccessible to the solvent. And that has to do with these things. Even if you just have a stretched out chain, there might be some residues that prefer to be in an alpha helix or something, but there has to be something more than just a little bit of secondary structure. And by the time there is at least one residue, and in this particular case tryptophan, that is completely buried and they have other residues around it, then we start getting to these concepts that we talked about, the molten globule, or for instance, you have some sort of hydrophobic things on the surface, hydrophilic things on the surface and hydrophobic things in the interior. And the cool thing with the TRP cage is that this protein is so small that people have even been able to simulate how it folds. And I'm going to show you that in a small movie. So I think this is the tryptophan side chain, and then you have a bunch of residues before and after it, and you can probably see what's polar here. So let's start the movie and see what happens. Do you see how quickly it collapsed? Instantly. And there's water around it here. And now it's searching here, and it's unfolding again, folding, unfolding. And eventually I think we'll get to a structure where you see the tryptophan buried in the middle and other residues surrounding it. And this probably takes something like, I think there we are. So here you actually see the tryptophan, but that's because we're not using space filling for all these other residues. So the tryptophan here is in the hydrophobic interior of the protein, and that has locked in the entire protein around it. And now it tends to stay folded.
How many residues?
You can probably almost count them. I think it's in the ballpark of 20 or so. I should know exactly, but I don't actually remember. Roughly 20. This was just a bit of piece to whet your appetite, what happens during folding. The other part, you see how flexible a protein is? This folds in a microsecond. Real proteins probably takes 1,000 times longer or 1,000,000 times longer. We also had a bunch of polar or charged residues. The polar residues frequently occur in loops or turns. Why? So, but why don't we want tons of loops on the inside of proteins? Yep. Well, so now we're in a chicken and egg problem, of course, but one problem with loops is that it's difficult to pair up all the hydrogen bonds in loop, right? So it frequently makes sense to have the well-ordered secondary structure elements on the inside, and then we have loops and turns and everything on the outside, on the surface of things, when we basically turning around and heading back into the protein. A membrane protein is even simpler. Then you have the helices in the membrane, and then you have the loops when you go out, and then you go back into the membrane. And for that reason, it makes, because they frequently occur on the surface of proteins, then it's really convenient to have polar residues there. Polar residues can hydrogen bond to water, certainly, but they can occasionally also hydrogen bond to the backbone of the polypeptide chain, which is important in a turn, because a turn will not have the polypeptide chain form hydrogen bonds with other amino acids, right? So suddenly you can have the side chain of one amino acid form a hydrogen bond to the backbone oxygen or hydrogen of another turn. Or sorry, of another amino acid.
So can you repeat
Sure.
about the polar
Hmm?
of the loop? Why is it more favorable?
So let's draw a protein. If I have a helix here, and then another helix here, and then it has a loop between them, this loop, by definition, doesn't form hydrogen bonds with its own backbone, because then it would be a helix or something, right? But that means that we're now going to have unpaired polar things here, both in the backbone and on the side chain. And they will have to form hydrogen bonds with something else. The question is, do we have something else here that is good for them to form hydrogen bonds with? If this is a perfect helix with just hydrophobic residues, that's not going to work. So then we need to place a secondary structure element so that we have other polar or charged things, maybe another loop or something here. So it can happen, but it's not quite as common. On the other hand, if we put them out here, a loop here, that's going to be very easy, because all these side chains can now form hydrogen bonds with water. So this is not, it's by no means impossible, but it's slightly less likely. And remember this thing that we talked about the hydrophobic effect last week, right? The first thing that's going to happen before you've even formed all these secondary structure is that we're going to try to pack all the hydrophobic things on the inside and the hydrophilic things on the outside. So they already start out on the outside. So I'm not saying that it's impossible, and I will not eat my left shoe if we see one, because we do see ones here. But it's, if I show you, say, a threonine, and you have to take a guess, where do you place it? If you don't know anything else, place it outside. But again, this is likelihood. This is certainly not impossible, but maybe 80-20. Charged residues are like polar ones, but everything is much more extreme. Charged residues do not occur in the surface. Sorry, they do not occur in the inside. So let's say that I show you my same beautiful new structure of a protein, the Lindahl protein, and then we place the arginine there. So what would you say?
No Nobel Prize for you.
That's likely not a very good model. There is something wrong in the model. And that has to do, I'm not saying that that can never be true, right? But it has the same thing with the free energy reason, that start by using paper and pen and the thing that sits on top of your body. Think about it. Again, there are exceptions. These ion channels I showed you, because suddenly I'm showing that there is a D there, and suddenly I'm much happier, because obviously suddenly it makes a whole lot of sense in this model that I place them right next to each other, so they will form a salt bridge there. But if it's just one, it's going to be so expensive that it can't happen. Of course, 1 time in 100 you would be wrong, but 99 times of the 100 you would be right based on that gut feeling, so trust the gut feeling. The exception, sorry, that's not so much an exception, but they still don't occur on the inside of proteins. They will occur in the surface. But there's one particular thing that happens with helices. Remember that we talked about the peptide bonds in the helix, and that each peptide bond has a dipole. Do you remember why? So let's see. If I draw N, Ca, C, N, Ca. Do you see how I draw amino acid backbones? It's always all trans, and then I start with the pattern NCAC, NCAC, NCAC. And when I draw that pattern, I start bothering about the rest. Then there must be a hydrogen there, there must be an oxygen there, there must be a hydrogen there, there must be an R group there, there must be an R group there, and there must be an oxygen there. And in particular, here we have a peptide bond, right? So that is the bond that's double that we can't turn around. So here we have a slight negative charge, we have a positive charge, slight negative charge, and slight positive charge. So there's going to be a fairly strong dipole pointing in that direction above each peptide bond. And in an alpha helix, what's going to happen is that all these dipoles, they add up because they're going to be pointing in the, it's a small exercise. Look at an alpha helix if you don't believe me. So they have one, do you see the hydrogen pointing there? The blue part is nitrogen and the white hydrogen. And then the next one there, and the next one there, and the next one there, and the next one there. So there are 3.6 of, and there you see the red oxygen and the green carbon. So all of these are pointing in the same direction from right to the left here. And there's going to be one per amino acid. So in a small helix like this, there are probably 20 or so peptide bond dipoles, and they all point in the same direction. And what happens when you put many dipoles next to each other? Well, they add up. So they form one much larger dipole that goes all the way from the right to the left. So this helix would have the same property as if there was a fairly large negative charge in the helix here and a fairly large positive charge in the entire helix there. And you see this delta, so that you can say delta minus there and plus delta there. But if we now take a negatively charged residue and put it here, they're going to love that because they pair up with the positive charge in the helix there. And same thing there, if we take a positively charged residue, in particular arginine or lysine, they're going to pair up with the negative charge here. So they effectively cap the helix. So how can you use this? So doing this with physics would be difficult. But this is implicitly what all your bioinformatics predictors do. If you do the statistics, if you have a helix and suddenly there is an aspartic acid, it's likely that that marks the end of the helix. And same thing with an arginine. It's likely that if the region that we start to have an increasing fraction of helical residues and suddenly there's an arginine, that is very likely the exact start of the helix. And that's what our bioinformatics predictors find. They're very good at finding these weak patterns. And that is also related to the thing I showed you about the membrane proteins in the first lecture, that the helices can actually use this to, instead of having an aspartic or glutamic acid here, this could be a pretty good interaction site for a negatively charged ion. And the other side of the helix would be a good interacting site for a positively charged ion. So then the book sums up a bunch of these properties. I so don't expect you to know all of these things about it, but you need to know the important thing that I talked about, because it's going to help you when you start looking at structures. So we can start to look about what properties they have, whether they have an NH group in the side chain. Proline is the only odd one out there. And then you can look in the side chain, do they have the C beta, and how many heavier atoms do they have? And then you can start, do they have a dipole? In case they are titratable, what is their pKa value? The pKa value is the value, the pH value, where we shift. And here you see in particular histidine, 6.5. Ugly close to 7, which means that it's hard to predict. All the ones that say 4.3 or 10 or 12 or something, they're going to be easy. So if it's 4.3 or 3.9, unless you're at very, very low pA, glue and asp are going to be negatively charged. And same thing with lysine and arginine. Unless you're at an extremely high pA, they're going to be positively charged. So do you ever have such low pAs? You do. And bacteria. So some of the ion channels we work with, that's actually a channel that is pH regulated. So it's usually open at pH 7, closed at pH 7 and opens at pH 4. So can you imagine a mechanism or something that would cause these channels to open or close? amino acids changing their titration states. That's how, because you can imagine that at very low pH you would have an amino acids that they are charged, right? And if they are now several amino acids with the same charge, they're going to repel each other. And now we change the pH so that they're suddenly neutral. And then they don't repel each other anymore. So nature tends to use these very simple physical properties to get things to move. Same thing, the movie about that channel I showed you before. We're going to come back and talk more about membrane proteins later. So why could it be good to have 3 charges on a helix if you wanted to move or do something? What happens when you put a charge in an electric field? There's a force on the charge, and that force will lead to a motion. So what electric fields do you have in your body? Nerve signals. They're tiny, right? Roughly what is the potential you have across a membrane in a cell? Yes, I would say to make life easy, 80 is probably better, but roughly 100 millivolts, and it's actually lower on the inside of the cell, so minus 100 millivolts on the inside of a cell. Is that a large or a small voltage? Compared to a battery, it's fairly low, right? But it's not the voltage that moves things, it's an electric field. And the electric field is voltage divided over the distance by which you have the voltage drop. What is the distance over which we have this voltage drop? 30 angstrom. So suddenly the electric field we have in terms of voltage per meter is roughly 0.1 divided by, let's say 5 just to make it easier, 5 times 10 to the minus 9. So the electric fields we have here is like in the ballpark of 10 to the power of 9 volts per meter. So it's not even mega, it's gigavolts per meter. Forget that the electric field here is far higher than the electric field you have around any of the high tension wires out there. So it's an insanely high electric field in your nerve cells. And then again, what this table also shows, I think it's a good summary. And of course, I expect you to know this by heart tomorrow morning. But you can also see here that here you classify things. This is common for have this just before an alpha helix, inside an alpha helix, or the after an alpha helix, in beta sheets, or in loops, or the core. And you see that there are some patterns here, right? Some residues prefer starts of helices, other prefers ends of helices, or the inside. Some residues much prefer loops, but they don't like to be in helices. Some of them prefer sheets, but hate helices, and vice versa. So already here there are weak patterns. And before we had so much sequence data, we tried to understand and predict secondary structure based on these properties, and it's worthless. It's so much easier to do this based on homology today. But overall, amino acids occur in places where they stabilize that structure, which is not obvious. But this goes back to Amphisen, that structures are really determined by physical laws. You could imagine the body designing and placing amino acids anywhere they wanted. But there is some sort of reciprocity. Amino acids only occur in places where it's good to have that particular amino acid, which starts to touch upon the things that how do proteins fold, and when do they fold, and what things can fold into a protein. Do you think already now, can any random sequence of amino acids fold into a protein? Do you have any idea how likely it is if I just create a random sequence of amino acids? Is it 50-50 or 1 in 10 or 1 in 100? We'll come back to that, of course, but you're basically talking about 1 chance in a billion. It's virtually impossible to create a protein of random amino acids. And why is an interesting question. I mentioned this a little bit when we spoke about beta sheets, but this is pretty cool. Both beta sheets and helices can do something, have something called a hydrophobic moment. Just as I draw the dipole, that you can think of a dipole as a moment from minus to plus, to show the way the charge is. Well, that is from minus to plus, but the other difference is that are things charged or not charged? And the same thing there, you can create some sort of moment that says, so what, do you have one side of a structure that is charged and another side of a structure that is not charged? So for a beta sheet, again, if we have this part with all the R groups, if we make all the lower side R groups here hydrophobic and all the upper side R groups here polar, then we effectively have one side of this sheet that is polar and the other one is hydrophobic. That is a very different structure from, you can imagine, take exactly the same amino acids and they all prefer to be in beta sheets, but place them randomly in this sheet instead. So you have the same composition, you have residues that prefer to be in sheet, but let's say that I place them in periods of 3 or something, or completely randomly. You will likely still have exactly the same sheet, but the sheet as a whole is not going to have any net property. It's going to be just as hydrophobic or hydrophilic on both sides. You can use this, you see the structure, this is actually an NMR structure. And you see that because in NMR you get many different structures, so that all these things are examples of probable structures. Do you see that there's one sheet here that goes from, say, yellow to orange? And there's a second sheet that moves from blue to green or so. And they're placed right on top of each other. So what if you create something here that the outside here is hydrophilic and the inside is hydrophobic? What you now just created is a small pocket, right? A small pocket that on the inside you can bind something that's hydrophobic, but the pocket itself is hydrophilic and soluble in water. And this is a FABP. It stands for fatty acid binding protein. So this is a protein that can transport fatty acids. And fatty acids by themselves would not at all be soluble in your cell, but we need to transport them to different points. So you solubilize fatty acids on the inside of this protein, but then the protein itself can move around and be quite soluble. You can do something similar with an alpha helix, but it's a bit more complicated. I like this. This is called a helical wheel. So first residue here, 1, and then residue 2, and then residue 3, and then residue 4. So I just place it. There is always 100 degrees between residues in an alpha helix. So I just place them spaced with 100 degrees. And in this case, we're moving, the helix is moving into the whiteboard. And here too, you can take residues that are completely happy to be in alpha helix and place them in random order. But I don't think we have placed them in entirely random order here. So do you see any difference between how things are placed here? All the black ones, they're hydrophobic. And tryptophan is also quite hydrophobic. And here you have polar things, right? And charged. So you could probably imagine having this part be soluble in water and that part be on the inside of a protein. You can probably even imagine 2 helices like this binding to each other, because you don't, tryptophan is bad because it's big and bulky, but isoleucine is a fairly small residue. So we could have this black part team up with another similar black part on another helix, and the 2 helices would get reasonably close. And let's see, I'm almost done here, so we're going to finish on time. I already touched upon this a bit, but this is basically just to sum up the whole point that the reason why I don't call them charged residues is that they might not really be charged. If I move beyond pH 4, the glue and asp might not really be charged anymore, but they can be charged on a specific pH. Same thing with lysine and arginine. The one thing to keep in mind here is histidine, because histidine will change its protonation depending on the surrounding. The problem is that it's not just going to matter on the pH. So you could imagine based on the pH of 6.5, well, then you could argue that histidine should maybe, if you're base the titration state exactly on the pH. There's one more complication in histidine, that we have 2 sites where you can be protonated. But the problem is that what if you have an oxygen right next to this histidine? then it's likely going to be more favorable to have a hydrogen in that position on the histidine. On the other hand, if we take this histidine and put it right in the middle of a protein, where there are no partners, then it's likely going to be less favorable to have a hydrogen there. So these pKa values, they are the ones you have for an isolated amino acid out in water. But what happens inside proteins is that things will shift around a bit, and it's even called pKa shifts, which we're not going to go through in this course. But you can, these are guidelines, but you can't trust them absolutely. It will depend. So how do we determine whether a histidine is charged or not? With great difficulty. We pretty much can't. And it's an outstanding, gigantic problem. Just trying to calculate pKa shifts is also extremely difficult. So having good predictors of pKa shift is one of the big outstanding in computational biology. I so wish I had an answer for it, but I don't. Once you have a structure, we can usually cheat. Because if, again, I can't see the hydrogens in an X-ray structure, there are too few electrons in them. But if I see that there is a big oxygen right next to it, I'm going to say, the hydrogen is on the left side of this histidine. Which is, of course, a guess. I could be wrong there, but in general, we're not. But in general, it's a problem that we haven't solved yet. And I already mentioned that. Oh, sorry, there we have it. There we have it. You see that we have a delta nitrogen and an epsilon nitrogen in this ring. So that we can choose to either protonate that side, or protonate that side, or protonate both of them. So normally you would have either the delta or the epsilon protonated, and then it's neutral. Or you have both of them protonated, and then it's charged. To make life even more difficult for you, this doesn't happen at exactly a specific pH, because this too is determined by the Boltzmann distribution, right? So as you go through a pH change here, you're going to start out from having something be 100% protonated, and then the probability gradually decreases. So suddenly you're 90, 80, 50, 10 eventually, and then at some pH you're so low so that you can start to assume that after this pH it's not protonated at all anymore. And how broad this range is, it varies, but it's usually in the ballpark of 1 pH unit, which makes it even more difficult for histidine, right? Because that if we are somewhere here, it's not just a matter of determining whether it's protonated or not protonated, it can be 30% protonated. How on earth can something be 30% protonated?
30% of molecules.
Yes, or as a function of that things exchange over time, right? So that the proton will somehow, it will bind a proton and then release a proton, and then it binds a proton again and releases a proton again. And the reason is, I so wish I didn't have to torment you with this, but the reason why this is important is that it's so related to binding charged molecules, protein stability, ion channels opening, DNA protein interactions are determined by charges, because you have all those charged phosphates in a protein. That electrostatic interactions are super strong, and when they occur, they tend to determine everything we know about that particular case. And that's, of course, why so many very, very large and famous research groups have spent decades trying to get better at predicting pKa values. We are far better today than we were 20, 30 years ago, but it's still not a solved problem. And we can't solve it with bioinformatics. I even have my pet channel here. So this is, you might start to see a pattern that I tend to talk about the molecules we do research on. So this is what the channel looks at low pH. Do you see that how things are pretty much repelling each other? And then what happens when you make a pH, and normally then you make a pH jump, and what will eventually happen is that when these helices get closer together, the thin pore here is going to become so narrow that this water channel here breaks, and then it can't conduct ions anymore. And at some point it's going to be entirely packed, and then the pore here is closed. And that is based on titration states of residues, we think. The problem is that we haven't, there are lots of titratable residues in this channel, something like 20 of them. And we know that if we change all of them, we can force it to open or close. We still haven't been able to identify one single residue that explains all of it. So this far, nature is smarter than we have been. We can even see it closing there. Look at the middle there. You're going to start to see that it breaks the water channel shortly. Do you see there? Now this part here, that there are two rings here of hydrophobic residues. And you see now there is no water anymore. And when there is no water here, it will not be able to conduct ions. So now it has actually closed. And this takes, I think, 2-3 microseconds. So still a very fast process. Many of them are much slower. Good. I think that's brings us to the end of today. This is mostly chapters 7 and 10. Skip chapters 8 and 9 for now, because that's going to be a bit of the physics that I think we will talk about tomorrow. What you need to understand of this is, compare this with the first lecture. The difference now is that now we need to understand the secondary structure in terms of enthalpy and entropy. And we need to just not just say that, oh, some things are more frequent in some places, but you need to understand why is it that prolines don't like alpha helices and why is it that glycine doesn't like alpha helices. And I think either tomorrow or it might be after break, we're actually going to start thinking a little bit more about exactly how the secondary structure elements form. Because we can learn a lot about their formation from the very simple F equals E minus Ts equations. And then I have a bunch of questions that we're going to go through tomorrow morning. But before that, you're going to have a lab this afternoon.
Yes.
Enjoy it. And then for Wednesday, we decided that while Dari can't be around, Björn and I will take that lab. So there are no changes in any of the schedules. So lab this afternoon, and then we'll meet tomorrow again. Good to see you.